Okay, let me now plot the associated picture for this sequential generalized Stangerle experimental setup. Now we have the following. There is an A measuring device, or if you want, A filtering device, or B measuring device, and a C measuring device. That's the first setup, and this is a preparation gadget, really, because you may send an arbitrary state and you select and filter out an A state. I don't put any index in here. In principle, of course, in the spectrum of the A, there may be many eigencats, many states. But suppose we filter out many and we just have this normalized state. And then, so actually what is here is that there are many possible outputs. Out of these, let me put a 0 perhaps. On purpose, I prefer this notation as compared to the books. It filtered this out and I normalized that. So I start with the normalized initial 1 and the eigenvalue is A0, therefore the information is that it is an A0 state. Comes through B, and B filters out a Bj out of all possible Bj's. The little j, perhaps I should plot a better, nicer picture because it is recorded. Well, we may have several others labeled by the little j index. We filter out the B capital J and reject all the others. And it goes through to C, and in the C we filter out the CK. Well, this is a bit dangerous notation I'm using, but I couldn't invent a better one because this is much better than the books. The books one is a little more confusing, and there may be others also here which are blocked, and they would be denoted by C sub little k. An alternative notation would be to call it K0 or I0. It's just one out of the many. And we may ask the following question. Let me pose the question and let's proceed to get the answer. But we are interested in the probability of obtaining that final CK capital with a capital when the beam coming out of the first filter is normalized to unity. Okay, I have already indicated all these qualifications. Okay, it's normalized to unity, the first one coming out of the first. There may be other states, of course, A sub I. How do we proceed to get this answer? So probability of getting the specific K is just one possible. K belongs to this set. Little k's may have many values, and capital K is just one value of it. What is the probability of getting this specific CK? If the initial one, if the output of a filter A0 is normalized to unity. That's an important qualification. So how do we proceed? It looks quite involved in principle, But if we really analyze it carefully, it is not that frightening. What do we do? In principle, you can do the following. You start with this input, because that's, as I said, a preparatory gadget. You start with this, after the A filter, this initial state. You know that it's normalized to 1. You can write it as a superposition of that C basis, the output of the C analyzer. P. This is, again, a dangerous notation, I know, but I couldn't invent a better one. All these A, B, C are Hermitian operators. They have its own complete orthonormal basis set, and this all output is normalized and complete. Therefore, I can expand this. I can write it as superposition in terms of those C, all of them. Okay, CK. So how does it look? Well, it looks as follows. I can focus on that specific K. Please exaggerate your notation so that you don't really confuse it. I use little k's and capital K. The capital K is a specific one out of the entire spectrum, which is labeled by little k index. Okay, there is this specific one with the weight factor pk and all the rest, which is different than the capital K. Okay. So what is really this pk? If you want to determine this, you just project the state on ck. I am trying to use the notation carefully so that you don't really copy it incorrectly. The meaning of this pk is ckA0. Okay. Then we again resort to the usual trick of inserting a complete set of orthonormal eigenstates of the B observable. As I said, they are all observables. They have complete and orthonormal bases, each of them. So I take this little pk is ck A0, insert here the bj and bj, which is identity, right? Associated with the capital B. So this becomes sum over little j, bj, ck, bj, bj, A0. But notice that in this particular setup, this beautiful, really experimental setup, only the capital J is filtered out, all the rest is blocked. So in this sum, in principle infinite, whatever, I have to isolate the J equals capital J term and write it as ck bj bj A0 plus J different than capital J, this is capital, sorry. I don't know what kind of notation I have to invent, because even myself, I may make a notational mistake in here. Okay. So what is the first term? First term is really the weight, little p. I denote the little p as weights and capital P as the probabilities. When you take the mod square of the little p's, you get the capital P. That's the definition of the little, right? So this is really K and J. That is, you filter to get the CK out in the last step and capital B sub capital J in the middle. So this is really the weight corresponding to that picture. And with the initial beam leaving A and entering into B is normalized to unity. That's what I call PKJ. So what is the probability of getting all these then? That is, I get to at the final stage CK, because that's really my starting question. What is the probability of getting the specific CK? But through this setup, that is between C and A, there is an intermediate B, which filter out the BJ, only blocking all the rest. So that's the reason why I go to the sub-weight, not the full weight, just focusing on this. So what is this then? The probability associated with this, which I denote with the capital K and J as little p K and J mod squared. And that is this expression, mod squared. So that's the answer to my question in relation with this sequential setup. The final is this. The initial is this via this intermediary. There's an intermediary in here. That's an important one. This is the result. Notice that all single indices are involved. Capital K, capital J, and initial one, A0. I put that A sub 0 in because that was normalized. I have to give it a special status to that one. Well, that is then, we can think of the following. Let us sum over the intermediate BJs. You know, it was labeled by that specific capital J, to consider the total probability of going through all possible B roots. Okay, let me write it in plain English, and then let's write the expression. And then I will compare it against a different setup. So, the statement associated with that state. Let me, read it again. Is sum over Bj, B sub little j to consider the total probability for going through all possible B roots. Total probability of going through all possible Bj roots. Okay. Would be obtained by taking that expression P, K, and J and summing over of that J, right? J was just a specific one, particularly picked one. This is the probability, and I add up all the probabilities. You see where I am shooting towards that. I am adding the probabilities. However, in quantum mechanics, it is really usually what you have to, what you are after is summing over the amplitudes and taking the full square of that amplitude. But here it is a specific. It's a specific decision I take. I first computed the probability for this setup for a single picked out selected root, and then I say let's sum over all the possible J roots and sum over the probabilities. I write the capital J first, and I will then change it to little j, because little j is an index scanning through the entire spectrum. Capital J is a selected one, so change it to j. That is a more proper language to use. So what is it then? CKBJ capital, BJ little, BJ A0 squared. Yes. Well, this is really addition of the probabilities. Yeah, just that. So what does this mean? This means we first record the probability of obtaining CK with all but the first B root, blocking all the rest. Then we repeat the procedure with all but the second B blocked, and so on. Then we sum the probabilities. The key word in here is sum the probabilities for this type of approach. Probabilities. Okay. And obtain that. We can rewrite it in several ways, right? How do we write it? First of all, what is the probability? This is CK, BJ, BJ, CK, BJ, A0, A0, BJ, etc. Because you take the complex conjugate and multiply with itself, and I put the associated expressions next to each other, right? So that is the expression I get. Anyway, this doesn't mean much. I have to. I made a slight mistake. Let me correct that mistake. This is one sum, and there's another sum for that. BJ, BL. And this is BJ and BL. And sum over here. In the second line, it is sum over J and L. Right? No, I'm sorry. I'm sorry. Let's leave it as it is. Just change this to J. I don't want to confuse you. No, let's leave it as we sum the probabilities. The next step is the following. Let's skip over the intermediate. How do I do this? Perhaps I can plot the picture again. Suppose remove B. B analyzer or B whatever filter. Then you have the following. A, again the initial arbitrary one came in and you filtered out A0 and blocked all the rest, and you normalize this one as before. Then you go through the C. That's the C analyzer. And originally, there was an intermediate B in here. We removed it. We take this beam, go to the C analyzer, C filter, and take the filter out to CK, again the same CK, that specific one, blocking all the rest, C and K, and ask the question of what is the probability in this case. Probability of getting CK in the same setting, that is, if the initial beam leaving the A analyzer is normalized to unity. So what is this probability? The probability, first of all, the weight I denote as pk. It is, as before, as far as this definition of pk is concerned, there is no difference. It is the same. You expand the A0 in terms of the full C complete spectrum and identify the specific capital K labeled one, and then find that weight factor in this expansion by projecting on the CK, capital CK, and you get that one, right? So it's the same. Yet, so I don't need this picture anymore, so I can erase it. Unfortunately, I wish I did not, but there's not room anymore. So, in this new case, CK A0 capital, I insert here, suppose I insert here a complete, although I removed the B analyzer, I am always allowed to insert identities, right? What is the identity? Bj. So sum over J CK capital. B little j, B little j, A0. Okay. And what is the probability is P K mod squared. Now this is what? This is the mod square of this. You take this expression, write it as J. You notice it's going to be, this is quite a subtle thing. I request that you pay due attention to this. That is the PK. And I have to multiply it with this complex conjugate. That's complex conjugate of this thing. Then I need a different summation in here, because that's a complete summation and J takes care of it. If I take the entire expression and takes the complex conjugate, I need a second index to express this insertion of another identity there, right? It could have been easier to see it from there perhaps, but anyway, you understand what I'm talking about. CK, BL, A0. Or finally, this is sum over J, CK, BJ, sum over J and L together. BL, A0, CK, sorry, write it here. Next. Instead of rearranging, I am writing as it is. I am sorry that I have to repeat this twice. Now you have to compare this expression against that one. With something which I erased before, let me rewrite it. What was its expansion? J how do I write this? First of all, I have to sum that. There is a summation over j, b1, b1. So that's a single summation indeed. Single summation, so it becomes j, ck, bj, bj, a0, and its complex conjugate. bj, ck, and a0, bj. You could write it in a slightly different fashion, but notice that this is single summation because you're summing over the pkj. You take the mod square and sum afterwards. Here, you carry out the sum and take the mod square afterwards. There, you are summing the probabilities. Here, you are summing over the amplitudes and taking the probabilities. Okay, so that's the difference. Sum over the amplitudes and take the mod square. The full amplitude is mod squared to get the probability. There you computed the individual probability and sum over the probabilities. That's an important distinction, and that reflects the entire subtlety of the quantum theory as compared to classical thinking. Really, here the quantum mechanical feature is fully reflected in this discussion, and there's an important question in here. I will assign it as a private homework, and please, I invite you to really challenge that. It takes another 5 minutes to complete it. The question is, there are two different expressions associated with two different sequential setup. In the first one, there was A, which was a preparation gadget, and then B and C analyzer or filters. And in the second, we had A preparation and a final C filter, and we ask the probability of getting that final C, with or without the intermediary. And we get two different expressions for the probabilities, and they look different. And one really is, when you sum, when you pinpoint a single intermediate one and then sum over the probabilities, that is obvious, that's from a classical argument. Question, under what condition do these two expressions become equal? So I invite you to demonstrate that if either A equals A and B are compatible, these two different probability expressions, I write it in full language, probability expressions, they are different. Expressions become equal when either A and B are compatible or B and C are compatible. It's sufficient to have any of these compatibility conditions. You don't need more than that. You don't really need, for example, that all three are compatible or anything. If either A and B compatible, obviously it would have a direct effect in the first one, because this state coming out of the B will be labeled by the two eigenvalues, the initial A0 and the second B sub j. And then it will go through the C analyzer with these two labels, A0 and B sub capital J. In the second one, there is no B, you are inserting it, and then after the insertion, you will need the information that A and B are compatible, so it's going to reduce. Both expressions will reduce, and then these two really tremendously different looking expressions will be reduced to the same form. Let me see whether I can give you the final result that you should be expecting to get. Well, perhaps I shouldn't write that down because that may be well, let me not write it down because then it may decrease the challenge of the problem. You may not wish to think as hard. Okay. You'll see once you go through it. Repeat my argument. The results, the book gives you the results, and I realize that it's a bit sketchy. It may be a little too much for the students who are exposed to it for the first time, because these setups are simple, but the arguments are quite complicated. But I gave you all the details in getting these two expressions in detail. So put these two informations, and then, for example, then what? In this picture, it won't be relevant, but of course, in the first picture, but the output of B will contain two labels, A0 and B sub j, and you'll see that. With that, you'll use orthonormalization properties of the A and C compatible operators, and the expressions will reduce to the same. And you may ask the following question. What was the source of difference between these two expressions for these two different settings, and what was the role of compatibility in sort of wiping out this main cause of this difference? Why AB being compatible reduced to the same expression, so whatever the fundamental difference was there to start with, it's wiped out? Probably that's a more challenging question for you to think than really driving the result, showing that the two results are the same. Okay. Now that takes us to the threshold of a very important subject, and today it's going to keep us busy for the rest of today and the remaining time of the second hour and the third hour. It is the so-called uncertainty relation, the heart of quantum mechanics. For many people, myself included, that's one of the metaphors of the quantum mechanics when you are talking to the public audience. If you would like to really make a resume of quantum mechanics, what is the state of the matter? Well, one thing that you may wish to mention is Heisenberg uncertainty, and second, some of you may not be a partisan of that idea. So the other one is the Pauli's exclusion principle, of course. There are many other things, of course, but this is the essential metaphors of the quantum theory. So it pays that we understand this uncertainty theorem properly. So that's what I will do next. Perhaps I can erase this portion. And I will introduce certain definitions before the break, and then we will express this statement, very statement of the uncertainty theorem. This is Heisenberg's version. And there are different variations, different versions of it. Particularly in the recent research field, quantum information theory, different variations and different versions of uncertainty relations are developed. But let's stick to the original, the simple version of it. It contains all the essential elements. So if you're really interested in going to the quantum information theory and working out the uncertainties for the entropies, etc., all the basic ingredients are in here. So what we do is we have seen that simultaneous measurement or sequential measurement of incompatible operators offer a lot of interesting, I don't want to call it magic, but magic features. There are so much involved in it, so that we should be able to get a theorem on the simultaneous measurability. If they commute, we know that they can be diagonalized simultaneously, therefore they can be measured simultaneously, as we have indicated. If they're not compatible, that's the starting point. We have two observables which are not compatible. And eventually we may wish to write it as I times a C Hermitian operator, because the commutator of two Hermitian operators are anti-Hermitian, and etc. etc. But let me not complicate the notation. Let's stick to the original things. So we define a new operator. Define. Well, I have to warn you that different books use different notation. So all you have to do is stick to the definition, the notation of the book that you are using. So I'll stick to the notation of Sakurai. This is not my favorite notation, however. So he says, define an operator. This is an operator now, which is A minus the A expectation value. This is a number, A being Hermitian. Expectation values are real quantities. Therefore, this is an operator minus expectation value. When you see a number like that, you have to always remember that there is an identity operator next to it. Okay, so it is by default understood, so we just do not write it explicitly, but you have to keep that in mind. Well, that's an operator. He doesn't give it a name, and he proceeds then to define the expectation value of the square of this operator. So you take the square of this operator, that's again an operator, and then take the expectation value. Although it's not indicated in the book, obviously it's clear that there is an expectation value already in the definition of this so-called variance operator, but anyway, dA, delta A. So there must be a state involved in here, right? Gamma or psi, whatever. So obviously, then you take the expectation value of the square of that operator in the same state, obviously. This you wouldn't think of an ugly situation that you compute this in one state and you go ahead and compute the expectation value of the delta A squared in another state. Obviously, that's not the case. That will be important in the further, the follow-up argument. So I put the same sign here and then I'll erase it. This is a warning saying that whatever expectation value, whatever state this expectation value is computed in here, it is the same state that you continue. You have a physical state, and then you have operators, etc. You define this. So this is defined in, let me give this a name. Well, following him, he gives the following name to it. He calls dispersion of A. Dispersion of A operator. As I said, different people would be using different language and notation, but this is Sakurai's notation. Let's stick to it. Well, let's first of all make an observation that this could be written in a slightly different form in the following way. This is equal to the expectation value. Inside there is A squared, and there is twice A and plus A squared. Some of you may say, wow, these are operators and you are commuting them. I'm not. There's an identity operator, a number. Therefore, it doesn't make any sense to write it as A times expectation value plus expectation value times A, because this is a number. Numbers can be put anywhere of the operator you like. So that's really twice. That's the inside. That's an identity times a number. So what do you have? You further go ahead and write it A squared, the first term. Second term, this is a number. It comes out automatically of the expectation value. Take the expectation value of this, and that comes out of the expectation value automatically, and the expectation value of the identity is 1. So then This is twice a squared with a minus sign, so altogether this becomes then. Okay, that's nice to keep in mind. Well, in certain cases you will need the positivity of this argument, this being the square of the expectation value of the square root of operator. Obviously it's positive definite, so this is positive definite. It means the a squared expectation value is larger than the a expectation value squared, etc. Anyway, for the time being, it doesn't do much good to us, but these are nice identities. Well, this explicit form already tells you that if the state in question, there are always states in here, if the state is an eigenstate of the operator in question, if psi is an eigenstate of A, that is, psi is A, then one of those AIs, then what happens? A expectation value, AI is AI, because UAct gives you AI, then AI normalized to 1, this is AI. Similarly, you have A squared on AI is AI squared on AI. Then you get the expectation value of this in the state. It is AI squared because this is normalized. Therefore, delta A squared in the AI state is AI squared minus AI squared, 0. So when you compute this dispersion in any one of the eigenstates of the A operator, the dispersion is 0. Because that's an eigenstate, meaning that expectation values are really the eigenvalues. That's an important observation to start with. Well, sometimes of course it depends on the basis, right? For instance, this general statement, let me illustrate this. Of course, when I talk about illustration, definitely we resort to the spin 1/2 problem case, right? Consider SZ squared, S squared SZ basis, which is SZ basis, or SC diagonal basis, which is plus minus Z. And you can also think of SX basis, for instance, plus minus, you denote it as plus minus X. We have constructed all those explicitly. You may wish to ask, what is the delta SX squared? Question, you say, in what basis? Well, you may wish to compute this in the, say, plus Z basis or plus X basis. Well, first of all, we have to remember that this is Sx squared minus Sx squared in any case. If I am computing this in the X basis, that is, it's its own eigenvectors, plus minus X, I will get 0, right? In this basis, you get 0 because they are eigenstates of the Sx. But if you compute it in the plus minus Z basis, what you get? You have to compute that explicitly. Let's do that after the break, and then we will continue. Well, of course, this portion is trivial. And you would repeat the same for the SZ, for example, if you were computing delta SZ squared. And the question is, again, which basis you are computing it. If it is the Z basis, or ST basis, it is 0. If you go to the X basis for that, then you'll get something non-zero. So bases play an important role. When you are talking about dispersions or uncertainties eventually, it is not the operators alone which play a crucial role. It's the operators plus the states they are in. You know, whatever that physical state or cat space is plays an important role. Eventually, we'll hit today, I hope, the minimum, so-called minimum are so uncertain. The states, it is the states which is going to play a central role in that discussion. So that's after the break.